Welcome back again. So, we have a now complete idea about 2 by 2 linear systems, its stability analysis and about the phase portraits and all that. Now, when we go to an n dimensional system, the things are not easy because there will be n eigenvalues, and according to n eigenvalues there will be certain eigenvalues which are simple, and there will be eigenvalues with algebraic different algebraic and geometric multiplicity. There will be complex eigenvalues which are distinct. There will be complex eigenvalues with multiple multiplicity, higher multiplicity. Accordingly, the decomposition of matrix is much more complicated, but this is again one can really linearly make it equivalent to another matrix, but there will be various types of blocks, what I call the block way of diagonalizing it. What we have seen in 2 by 2 systems, we have 3 types of block. One is in the diagonal form lambda 0 0 mu, the second one is the diagonal form is lambda 1 0 lambda, and third one is of the form a minus b b a. Now, we are going to have different types of blocks according to the multiplicity and things like that. We will appeal to the Jordan decomposition theorem, and later you will see that there are typically 2 types of blocks, but that 2 types of blocks can occur in different ways with a different order, and that is a difference. And then each of that blocks computing your exponential is easy, and that is what we are going to present here. For example, when n equal to 3, you have 3 eigenvalues, In this case, the only possibility is that all the 3 can be real, or one can be real and other 2 will be complex conjugates. These are the only possibilities will come. So, a typical block matrices will be equivalent to something like that. You can have the form, it may reach the form lambda 1, lambda 2, lambda 3. So, you may get block of this form. Typically, this is the case, you have eigenvalues, 3 eigenvalues with 3 eigenvectors, you will have that. So, you have the main issue is that the lack of eigenvectors. It can be of this form, but another form, it can be lambda here, lambda 1 here, and then another one lambda 2. This is a block of this you already studied. You can have a block of this form, and here you have 0 0 0. This is a case, you have a block of that form. You will also have a block of that form, another one lambda 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 0 0 here with all diagonal elements 1. This is another block of this one. Typically, these are the blocks you are going to get. High dimension, it will be complicated, you will have different multiple of blocks. And other type of block, these are the cases where you have real eigenvalues. Another one real and one complex, you will have an eigenvalue of this form, and you have a block of this form a minus b b a. You will have 0 here, 0 here, 0 here, you see. And all these things you will see that you can see that you can compute e power b. So, I will give an exercise here to start with. You consider this type of systems, you take B1, B1. So, you consider this system with B1. The exercise is work out all possible cases, work out all possible cases with the above matrices, possible cases with the above that systems. So, you can write down your system, wide system with respect to B1, B2, B3, B4 areas thing, and see the trajectories how it will look like. Okay. And sketch the portrait, and sketch the phase portrait if possible. So, we will start with an example here. example, an easy case. A is of the form with a diagonal form 0 0 0 1 0 0 0 minus. This is a decoupled system, already in the decoupled system. So, two eigenvalues lambda 1 equal to 1 and lambda 2 is equal to minus 1. So, here you have your multiplicity, algebraic multiplicity 2. Luckily, it is in that format, you do not know. So, it is a decoupled system, you can write down your solution immediately. x1 t is equal to x01 e power t, x2 t is equal to x02 e power t, and x3 t is equal to x03 e power minus t. You see, this goes to plus or minus infinity as t tends to infinity, this goes to plus or minus infinity, but this goes to the origin 0. So, how does it look like? So, if you look at your x1 x2 plane, you will have unstable node type thing. So, forget about the x3 component, look at only x1 x2 plane, it is something like a node, because x01 e power t, x02 is nothing but straight lines in the x plane. So, that graph, if you are if you are looking only your initial values are in the x1 x2 plane, if you are starting an initial and third component 0, then by this thing third x03 is 0, x3t will be 0 for all t, and hence if you are starting a solution in x1 x2 plane, it will remain there, and in that case it is a node type singularity. So, explain the node type singularity, and these are straight line because you have the same eigenvalue 1. On the other hand, so you will get your and which is also unstable in this particular case. So, you will get EU is equal to x1 x2 plane, that is your unstable thing. And if you look at it, x1 x3 plane, you have one eigenvalue 1, again it is all these are all decoupled system. So, x1 plane you have the eigenvalue 1 and x3 corresponding to that you have eigenvalue 1. So, you have your saddle type actually, saddle type, and you will this is the same thing when you look at it x2 x3 plane. So, if you look at these trajectories restricted to these planes, the trajectories will remain there itself, and you will have again the saddle type, and your stable part, and which is stable because you have minus 1 as the eigenvalue, which is not stable, sorry, it is a saddle type and you do not have it. But if you look at only the x3 axis, if you take something a point initial point in the x3 axis, that you will get a stable space. So, you will have x3 is the stable subspace, this is the unstable subspace, and this is x3 stable x3 axis is your stable subspace, which is one type. Now, let us try to plot these things in let us try to plot. So, let me plot this, this is my, if you do that one. So, this is your x2, this is your x1 and this is your x3. So, if I so you can extend, of course you can extend like this. So, if you extend your x3 like this. So, let us look at only x2 x3. So, when you look at x2 x3, you have the saddle point. So, the trajectory will be there and x2 goes to infinity. So, you will have this thing, and this is your x2 x3, correspondingly this is your x2 x3. So, you will have the trajectory will going and this trajectory will go here, you see. So, that is a corresponding to x2 x3 plane, so this is your x2. So, you see, similarly if you look at it x1 x3 plane, again it is a saddle point type. So, you will have this one which is going to x1 going to infinity. So, you will have your x1 x3 if you go here. So, you will have your trajectory something like this. Okay. So, again x1 going to infinity. So, the trajectory will move that. So, that is in the x1 x3 plane. Now, let us look at the x1 x2 plane. In x1 x2 plane, the solution if you plot is a straight line and which is going to infinity. So, if you start from anywhere, so and it is a straight line. You see, you have your straight line. If you plot it here, you will have plot. So, let me with a thing. So, this is the x1, the axis will be, of course, if you start an arbitrary point, accordingly it will behave. So, whenever you start a point, it will give you a trajectory, and if you project that to the plane, you will see that saddle point way of behaving it. Okay. So, let me put it a different color also for this thing. So, let me put a different color. So, you have that, you see. So, that is a complete picture about that plane. This is the phase portrait will look like, what the graphs and the curves are given on the respective projected planes x1 x2, x2 x3 and x1 x3. Okay. So, you will have all that kind of picture. So, if you start arbitrarily, it will move accordingly. So, now with this one and maybe one more example to give you, so that you slowly get used to it, how things will be. 3 dimension you can do this little more with a little more imagination. I am going to take a matrix which has some complex eigenvalue. So, the best way you know that the complex eigenvalue, you have minus 2, this is A, B minus B, B minus B minus 2. So, I will take 0, 0, 0, 0, anything 3. So, if you do this one, so you see the corresponding to you have a system, you see this corresponds to a 2 by 2 system, this corresponds to a single system, and this gives you, the first part gives you a complex eigenvalue. So, you can do the exercise again, each time you can do the exercise. Eigenvalues are minus 2 plus I, of course minus 2 minus I and 3, you have these eigenvalues. So, what you do is that you already seen this one, this is already in a decoupled form. So, 2 by 2 system, the x1 x2 plane, here is like a focus, like a focus. You have to see that I do not classify because like focus if you take only x1 x2 plane, and other things you have to see that one. So, if you look at here, if you are trying to do the phase portrait of this one, so you have your phase portrait of x1 x2 plane. So, I have my x1 x2 plane like this. So, if I take any trajectory, so you have here, this is my x1 x2 plane, this is x1, this is x2 and this is the x3. So, if I start any point here again, it is a decoupled, the x1 x2 plane and x3 part is decoupled because of this particular form of A. So, if I start here anything, any point here, if I start, it will remain again. So, if I start anything in x1 x2 plane, that means the x3 coordinate is 0, and by looking at the way we constructed your matrix and solution, it is a decoupled, the x3 is part component is decoupled, and hence it will remain in that plane itself and it will behave like a focus. And since you have minus 2 as the real part of the eigenvalue is minus 2 in the other case, which is a converging thing, it converges. So, if you start from here, it will remain in the plane and it will come something like that, it will, and you have an orientation according to the sign of P. You see, you have that writing. So, the trajectory, this is the x1 x2 trajectory plane. But on the other hand, Now suppose I start a point from anywhere arbitrarily. What will happen? The x3 component, the eigenvalue is 3. So, the x3t will be x03 into e power t. So, the x3 component as t tends to infinity, the x3 component will tends to infinity, but then x1 and x2 is something like a focus. So, it will move around that one and the move around the its axis, but then moves away along the x3 direction. So, if you do this thing, so if you start from anywhere other than in the plane, so it will move like this. It will go around that thing, but at the same time x1 and x2 it will move and it will become smaller and smaller around the x3 axis, because x1 and x2 go to 0. It is x1 and x2, the real part will go to 0. So, it will move around the x3 axis and move and go up, but the amplitude becomes smaller and smaller. And on the other hand, instead of -2, if you replace 2 and it will be diverging. So, again then it will be move around like that, it becomes larger and larger. So, that is how you can focus, you can sketch the graph according to the model. So, we have two examples are given. One, you have the focus behavior on a restricted plane, on another example in which you have a saddle point behavior. You can give all kinds of things with the node and all that. So, we will skip this, we will do only that one. Now, we will go to the general case and Jordan form. General case, typically you want Jordan form. I am not going to explain the Jordan form in detail, that you have already studied in the either preliminaries or you also studied in the general linear algebra course. So, Jordan form typically says that you look for all the eigenvalues. According to eigenvalues, you have to classify the real eigenvalues, you have complex eigenvalues. And then if you, the idea is that if you have an n by n system, you essentially need n eigenvectors. But if there is an eigenvalue, if all the n eigenvalues are all distinct, whether real or complex, if you can produce n, you have the diagonalization. But then there will be eigenvalues, real eigenvalue with algebraic multiplicity, but less geometric multiplicity, and then you may not have enough eigenvectors to diagonalize. Then the idea is to look for what are called generalized eigenvectors studied in your preliminaries. And according to the deficiency between a geometric multiplicity and algebraic multiplicity, you will be having a lack of sufficient number of eigenvectors. And this makes, just like in the previous case 2 by 2 system, when you have an eigenvalue repeated twice, you got a block of the form lambda 1 0 lambda, and which is not diagonalizable. So, now as I said in n equal to 3, you have all kinds of things, but what Jordan decomposition tells you that every matrix A, if you start with, so A, you can linearly can make it equivalent to a diagonal form, not with a diagonal matrix, diagonal with entries with blocks B1 etc. some number BR, you can have the blocks, each BI will have some order, these are all belongs to certain multiplicity and other thing. So, you will be able to write this matrix B1, you will have some order matrix say K1, and B2 will have some order 2 and etc. BR will some order Kj. Of course, K1 plus K2 plus etc. Kr will be equal to n. So, the total order will be n by n matrix. How does my B looks like? That is more important. The idea of that, if you want to solve your system, so if you have, this is called my B, big B. So, if you want to solve your system Ax equal to y, because of this diagonal form, it reduces to, it is enough to write down your solution, enough to solve the system of the form each one. So, if you want to do it, you can have a transformation P and P inverse, here also it exists, but essentially reduces to study each Bi a subsystem which may be of smaller order, and this also Bi has some special forms which I am going to describe here. So, it is enough to study Bi of some Yi, the is equal to something. So, Yi dot is equal to Bi of y, you can have solving for I equal to 1 to r. Okay. And each Yi is a vector corresponding to k by k vector, kj vector, if ki vector, if Bi is of order ki by ki, k by ki cross ki matrix, then Yi is a vector of order ki, is a ki vector. So, you can solve for all these things. So, a bigger system eventually reduced to solving a smaller system. How does Bi takes the following two forms? Bi takes the following forms, takes the following only two forms, that is a whole interesting thing, following form. So, it will be of the form some lambda, the diagonal entries are lambda, and the off diagonal entries will be 1, the remaining will be 0. This is the case corresponding to real eigenvalue, corresponding to real lambda, and it will take the form, or it will take the form, the following form, that is another form. It will take the form d etc. d, and here I2 of this itself, this block itself is a block, each one is a 2 by 2 block, everything is 0. And what is d? D is of the form A minus B. See, this is a familiar form, eventually reduced to everything, and I2 is a 2 by 2 is an identity, 2 by 2 identity, 0 0 1, you see. So, each block, the only thing is that in the A, B, there are different blocks B1 etc. Br, each Bi will have different orders, and according to the eigenvalues, whether it is a real, it takes this form or the form D is equal to I2. So, this is again the form is a block consisting of 2 by 2 blocks. This is corresponding to complex eigenvalue, corresponding to complex eigenvalues. So, it is enough, essentially it is enough to how to know to compute in theoretically, it is still difficult, theoretically it is enough to know how to compute the exponential of these two type of matrices, which is what I am going to do it right now. Okay. So, you want to, so I call this is equal to the form C1 for the computation with this I call it of the form C2. So, I want to know how to compute C1, how to compute e power C1. So, now consider this case, we are going to do that one. So, C1, so look at C1, C1 I can write it separately as lambda, I separate this one lambda into identity, if some order whatever it is plus n, I write that one. So, look at here, I separate this one, I keep only the diagonal entries, put 0 0 everywhere, plus I put diagonal entries also 0 and put 1 1 1 as the off diagonal. Okay. So, where some order, I have not told what is the order depending on that, where n takes the form diagonal entries also 0 1 1 etc. 1. The rest of the elements is, you see, it has a very nice matrix. Here is a small exercise again for you. You have to keep on doing that exercise. Assume C1 is of order k. I told you it will be some order. I assume C1 is of order k. Of order k. So I is an identity matrix of order k by k, and n is a k by k matrix. Okay. Exercise is that show that n power k is the zero matrix, and n power k minus 1 is not a zero matrix. Just compute n square etc. If you want to compute either by induction or you can compute that one. Such type of matrices are called nilpotent matrix. So, you have a matrix, any matrix. So, let me matrix any matrix Q is said to be nilpotent, of order k if k is the first instance where q power k is a zero matrix and q power k minus 1 is not a zero. That is the first instance. Of course, if q power k is 0, that implies q power k plus 1 etc., q power x plus k plus 2 etc. 0. So, that makes the computation of matrices is easy, because you do not have to compute after k onwards. So, the exponential term, exponential of nilpotent matrices reduces to a finite sum immediately. Therefore, e power q, so the computation of a nilpotent matrix is easy. E power q will be identity plus q square by 2 factorial plus, of course, if k is large you have to do a large thing, still lot of work, but it is finite. So, you do not have to worry about anything else, you see. So, that e power q, after that everything is 0, because q power k is equal to 0 implies q power k plus 1 equal to 0, q power k plus 2 equal to 0, it goes on to. So, you have the nilpotent. Our aim is to compute e power c1, e power, we want to compute e power c1. Of course, e power c1, as I again remarked earlier, if you have two matrices, now c1 is of the form two matrices lambda I plus n. So, if you want to compute e power a plus b is equal to e power a into e power b, then e power a plus b is equal to e power a into e power a b if a and b commute. The interesting fact is that in this case one of the matrices is identity, hence identity and n will always commute. Any matrix with an identity matrix will commute, hence further lambda I and n, this is a trivial fact, and commute, that is an important thing. If there is no commutation you can write. So, e power c1 will be e power lambda I plus n. Since this commute, this will be nothing but e power lambda I plus into e power n. So, you have immediately e power n, and e power n you have already the formula. You have already the formula for e power n. Okay. So, you have your e power n. So, in particular, so further, so you are interested in computing e power t c1, because you want to find the solutions corresponding to c1. Okay. So, that is e power t c1 will be e power lambda t lambda in e power tn. So if you do a simple computation, it's immediately, I will go to the next page. So e power c1 will be equal to e power lambda I into e power tc1 we want to introduce. So you will get this as, if you do this one, you get e power t lambda into e power tn, and that immediately can be written as e power t lambda. So you have a complete thing. If you do, because t will change the thing, you get 1 t square by 2 factorial etc. up to t power k minus 1 by k minus 1 factorial, then 0 1 t, the last element will be t power k minus 2 by k minus 2 factorial. So if you go like that, the last but 1, the last here 1, and the last element row will be 0 etc. 0. So you see, so you have an immediate solution. So for the system with C1, if you go back to the system with not this one, next one, so C1, yeah, if you go to the system with the C1 here, you see, so you want to solve the system. So you have that, this is a system, a particular form of the matrix. These are the only two things will be coming up. So if you go here, so if you want to solve your system y dot is equal to C1y, this will immediately implies your yt is equal to e power t lambda into e power tn, this matrix e power tn of y naught. See, so you have your solution. You have a nice solution here. Now we go to the next case, second case. Another one is of the form C2. C2 is again, you can write it as in a nice way, but not with an identity. You will write only d on the diagonal. You write your d here, 0 here, 0 here, plus on the off diagonal, these are all 2 by 2 zeros, 0 etc. 0, this is 2 by 2 0, 0, 0, I2. So you go here 0, the last but one, the last element will be I2, and then you have 2 by 2 things, 2 by 2 you will have 0. So you see, so this is what, again you can write this is a 2 matrices, and this can be written as something like you call this diagonal of DDD plus some n, where n in this form is, so let me write it R. So you can write this here, again these things are commuting, you have the commutation, there is no problem. So if you write your solution with a little computation, I will skip here, with a little computation, which is an exercise, little computation, the similar thing, computation, you can write your e power t c2 is equal to, so is that matrix is of the form, what is the matrix? E power at, okay, into, everything will come 2 by 2 blocks, R, TR, etc. t power k minus 1 by k minus 1 factorial, R, 0, R, TR, etc. up to that, and the last element will be R. Last element will be 0, last but 1 will be last element. Yeah, is correct R. So you have yes. And what is R? R will be of the form the same formula, your cos bt minus sin bt. You see, only thing you are not able to separate it, cos bt. So you see, again you have your solution yt. If you have the solution y equal to c2y of this form, your solution will be of the form y2 is equal to e power a t into this matrix, whatever it is. Okay, yeah, this matrix, what do we call it, whatever it is, this matrix into this matrix into your y naught. So you have your solution representation again. You see. So that gives you more or less a complete description. Of course, the things are not that easy as we think, but then you can write your solutions completely here. You are able to completely here. So what the important point in this thing that for every solution you are reduced to a system of smaller systems, and the only things are coming is the exponential function in the solution, the polynomial functions because of t, t square etc. polynomial functions, and the trigonometric function. So the every solution of your linear system is a linear combination of these factors, something like t power k, e power a t and cos bt, or t power k, e power a t sin bt. So the only these elementary functions and its combinations will come in the representation of these solutions. That is a small remark. So maybe we will write a corollary in that form. Immediately what analysis you can do that, the solution xt, the solution xt of the initial value problem, this is an important observation. Initial value problem is the linear combination of the form t power k, some number t power k, there will be many different types but it will be of that form, cos bt and t power k, e power a t sin bt. Okay. So this also where lambda is of the form a plus ib. Okay. Of some form. So that gives you, so you know that only the expressions of the form t power k, e power a t cos bt or sin bt are available, and so you can immediately see that you can occur stability only when a is negative for all the eigenvalues. So the stability of this system, if one of the terms, the real part of the eigenvalue is non-zero and positive, greater than or equal to 0, if any eigenvalue, any one of the eigenvalue has a real part which is greater than or equal to 0, you do not have the stability. So the xt goes to 0 only when the real eigenvalues, all the real part of the eigenvalue is negative. In that case it goes to the origin exponentially because there is an exponential term, and that is what the one remark. And secondly, what you want to do is that you want to do one or two examples at this stage. Maybe I will give you one more thing, one more remark I want to make it here probably. The other remark I want to think, so corresponding to that, I do not prove here, but I want to make in the general case what will happen is that So, you look at this, all the subspaces ES is equal to the span of, I am writing in general complex. If the complex part is 0, you will become real part. So, you look at Vj, Uj, where Uj plus Ivj is an eigenvector corresponding to lambda. So, okay. So, such that your Eaj is negative. Okay. You look at your eigenvalue is always lambda is equal to Aj plus Ibj. Okay. And eigenvector, this is the eigenvalue, and eigenvector is equal to Uj plus Ivj. You write it that way. In the complex way, you write everything. So, you have, if Bj equal to 0, it becomes a real eigenvalue, there is no vector. So, there is no problem. So, it incorporates even the real eigenvalues with Bj equal to 0. So, look at all the eigenvalues, all the eigenvector, real and complex part of the eigenvector corresponding to a real eigenvalue, corresponding to an eigenvalue whose real part is negative, and collect all that, span it, that are called the stable part. Okay. And then similarly, you have your EU, this is span of Vj Uj with Aj positive, and EC, which we are not seeing an example, maybe we will see an example, span of Vj Uj with Aj is equal to 0. What the interesting theorem will tell you, which I do not prove, the your space Rn can be decomposed into Es. These are called direct sum EU, direct sum of course, one may need to use the other EC. This is called the stable space. You will learn more about these things in the nonlinear study. Stable, this is the unstable subspace, unstable, this is called the center. What I have not mentioned here is about the generalized eigenvector. Once to do the Jordan decomposition, as I said, you may not have the enough eigenvectors. So, one has to work with what is called generalized eigenvector. So, we will be studying in that the whole analysis in the generalized concept, which we have not introduced, or we do not have time in this course to get into more details about the generalized eigenvector here. But we have to work this decomposition to happen in that form, in Jordan decomposition to happen, you need to work with the generalized eigenvector. So, we will not give you, maybe probably if we have a time I will do. The interesting one more thing is that some of the notions I am introducing it, you will understand it when more about it when we go into the nonlinear analysis. Okay. A definition to start with: a subspace E is called invariant under the flow, recall the flow, called invariant under the flow. What is flow? Flow is e power Ta. If e power Ta of E, if we act on E, it will remain in E itself. So, it will remain in E. The other results about the proposition or theorem, part of the previous theorem, which I have not stated, is that these spaces are invariant. E power Ta of Es contained in Es, e power Ta of EU contained in EU. What it shows that if you start with a point in say e power s, and if you follow the trajectory starting from there under e power a, it will remain in e power s itself. It will not move out of e power s. On the other hand, that is a stable space, subspace. On the other hand, if you start with from a initial point from e power u, then e power ta of that element will remain all the time in e power u. So, it will not leave these spaces, that is invariant thing. So, the e power s, e power u are invariant subspaces under the flow. So, the flow will not do that one. In particular, if x naught is in e power s, you can see that e power, that means all its real part of the eigenvalues are negative, and hence it is stable exponentially. So, if you start with an x naught in e power s, e power ta a has negative eigenvalues, the trajectory will go to 0. That is an interesting thing, okay. And this is in more general, probably you may learn in the form of stable manifold theorem, which we will not do it here. Probably we may do it in a module of nonlinear analysis if possible, otherwise we may not cover, but basically it is the content in the linear system of that. The stable thing, anything you start from a stable manifold, stable subspace, and then you do not get the subspaces when you go to nonlinear analysis. You start thing, but in the linear system, if you start from the stable ES, it will go to the thing here. To give a probably I want to give some more example, one more lemma or something. I may skip it here, but then I want to start 2 more examples in the remaining time of this lecture. Maybe 1 example or 2 examples, let us see, we will give 1 more example. So, let us start with an example now here, and maybe 1 more example in the next class we will do it thing. So, with this example we can think. So, let us consider the system A. 0, minus 1, 1, 0, 0, 0, 0, 0, 2. If you look at the system A, this is again actually decoupled into a 2 by 2 system here. If you look at here, this is a 2 by 2 system decoupled with A equal to 0. So, it is a something like a center, you see, and then x3 component is separate. So, what are your eigenvalues? You have your eigenvalue I, of course minus I, the other eigenvalue lambda 2, and you have lambda 3 is equal to 2, lambda 2 is equal to yes. And you can also see that your eigenvector, you can see that these are all exercise. Whenever I leave, I do not work out, is called the exercise part. You have your 0, 1, 0 plus I into 1, 0, 0, and that we will call it, this is your u1 plus IV1, and you will have corresponding to this you have another vector u2, because that is a real eigenvalue. So, you have only one eigenvector 0, 0, 1. So, you see, so you have. So, if you look at it here, this part is 0, it is a corresponding to a center. Your EC is nothing but your x1 x2 plane. It is a center, it is a form of a center with the real part of this eigenvalue is 0. So, for this lambda 1 lambda 2, the real part is 0. So, it will behave like a center, and your other eigenvalue is 2, that is corresponding to the x3 part, and since it is a 2 and positive, it will go to infinity and it is unstable, and you have your unstable part is the x3 axis. You see, so always decomposing, and you are, there is nothing like stable here, stable is empty. So, you again complete the x1 x2 plane and decompose your R2. Of course, your R3 is EC plus direct sum into EU. ES is empty. So, you plot this graph here if you want to see a plot of this graph, you want to see a plot of this graph, so this is your x1 to your x1 and this is your x3, and x3 is a decoupled part. So whenever you start a solution here, because x3 in the x1 x2 plane, so if you have any initial values in the x1 x2 plane and by the solution is a decoupled, x3 is decoupled, it will remain in the x1 x2 plane itself, and in the x1 x2 plane the real part of the eigenvalue is 0. So it will remain like a center, so it will be a circle, the solution will be circle. So if you start from here, it will be like this, you see it will be in the x1 x2 plane. So what will happen if it is a point, if you are starting from above or below, what does it shows that? This shows it will rotate, the x1 x2 plane it should rotate, but then the x3 component, x3t is equal to x03. If you look at here, x3t is nothing but x03 into e power 2t, it goes to infinity without reducing this thing. So if you start from any point here, if you start from here, it will move like a center, but then xt will going up, you see. So if you anything, it will curl around with the same like a center and will move up, because that if you have below, it will also move below with the same radius. So it can work, the exercise for you to take all kinds of things in 3 dimension and see all possibilities. Okay. So maybe one more example to, and then in the next class I will give one more example if I have time. So one more example I want to. So the examples are the best way of imagining. So I want to have A with the both, we already seen with one eigenvalue 0. Now you have one with both eigenvalues 0. See. So what is this system corresponding to that? x1 dot is equal to 0, x2 dot is equal to x1. So that implies immediately x1t is equal to constant, that is nothing but x01, and your x2t is equal to x01t plus x02. So now let us find out the equilibrium point. If you want to find out the equilibrium point, you look at Ax equal to 0. When Ax equal to 0, the first won't give any information, because x 0 equal to 0 you will get it. The second will give you an information, the first component is 0. So the first component is 0, second component is arbitrary, that implies every point, earlier we got every point on the x axis, every point on the y axis is an equilibrium point, you see. So if you try to see the here, plot the graph here, all the points here are equilibrium point. If you recall the earlier example which I have given, in a similar situation with an eigenvalue with one eigenvalue 0 and other eigenvalue non-zero eigenvalue, you have seen that all the points on the x axis thing, and anything you start above it goes towards that thing. But here you will see something different. So when there is a degenerate case, the situation will be different. So now let us look at it, any point x naught here. Again, what does it say that? This tells you that again x1t is x01. So, it should remain in the perpendicular line still, and the second one, because of the x0 to t, this looks as it depends on this t tends to infinity. You say x0 1, if you take x0 1 in this is a quadrangle, on this quadrangle x0 1 is always positive, you see. So, if you look at your first if you take the upper half plane, the first and second quadrangle, your x0 1 positive or x0 2, yeah, if you take this, sorry. So, if you look at this portion, your x, this is the x1 axis. So, on that portion, on this portion here also x0 1 positive, x0 1 is positive, and if you look at here, in this case x2t here tends to plus infinity as t tends to infinity, if x0 1 positive, and it tends to minus infinity as t tends to infinity if x0 2 is x0 1 is negative. So, if you start any point here, the first component will retain here. So, it has to move in a line perpendicular to x1 axis, but it should move to plus infinity. Even from here your x0 common component is positive. So, it will not go towards any equilibrium point. Anywhere you start it, it will move like this, it will move again like that only. On the other hand, this side x0 1 is negative, in that case it will go to minus infinity, the thing, and again it should remain in the perpendicular to x1 axis. So, it will move here. If you start from here, it will move, you see, near the center the behavior will be like this. Anything where it starts does not matter, even if any point you start it will move like that. And these are all equilibrium points. Also on the y axis, if you start it, it will remain there because every point is an equilibrium point, and the right side if you start it is going to the infinity along that one. So, this is a phase portrait of this thing, of this system. So, with this we will have finished more or less everything with one definition. I will end this class. Definition: if all the eigenvalues of A, this is because this terminology will be used in the nonlinear system, if all the eigenvalues of A have non-zero real part, have zero real part leads to center, that is why have non-zero real part, then the flow is said to be hyperbolic. Then the flow is said to be hyperbolic, and the system is called as, and the system is called a hyperbolic system. So, you will study more about this hyperbolic system etc. in the nonlinear thing. Okay. So, in the last lecture, if we have time, we will try to present one more example, but then aim of my next lecture, the last lecture of this particular module, is to see how to represent the solutions in the non-homogeneous system. So far we were studying x dot equal to axt. So, we want to see how to use this to represent a solution of the form x dot equal to axt plus gx, and we make few remarks when it is a non-autonomous system where A depends on AT. then we do not have a representation like that, but we can represent a solution in the form of something else, what are called the fundamental and transition metrics. So, with that we stop this lecture. Thank you.